Hello everyone, this is Group Chapter 5. Our team members are Wei-Chen Huang, Ming-Chi Zhou, Chu-Yun Guo, Seka Ip, Yili Xiao, Xue-Ying Yan, and Jason Shafruddin. In this chapter, we are going to talk about one-way table, two-way table, chi-square, F-distribution, and correlation.
Now I'm going to talk about the one-way table, which is one of the tables we use for chi-square test. Here are the formulas for one-way table. Chi-square equals the sum of e minus o squared divided by e. Sometimes the expected value is not given, but we can find out the expected value by using the formula E equals n times p. And the third formula we use is df equals n minus 1, which is used to look up the chi-square table on the chi-square chart. Here are the steps for one-way table to test the claim. Step 1. Write down HO, which is probabilities are equal to the claim. HA, at least one probability is not as claimed. And step 2, shape the rejected region. The shape is always on the right, and we find out the value of chi-square table. Step 3, calculate the chi-square curl. And step 4, draw the conclusion. Let's do one example together. The question is, students were given the same test 10 times. It is expected that 10 students will pass the first time, and the number will increase by 10 for each child. The following chart shows the observed values. Constructed a test for hypothesis that the expected percentage are the same as observed. Here's the solutions. First, we have to calculate the e minus o squared divided by e for each child, and we draw the HO, and we write down the HO. P1 equal 0.018, P2 equal 0.036, P3 equal 0.54, P4 equal 0.072, P5 equal 0.090, P6 equal 0.109, P7 equal 0.27, P8 equal 0.145, P9 equal 1, P9 equal 0.163, P10 equal 0.181, and HA is at least one probability is different. And then we shape the rejected region, and then we can look at the chi-square table to find out chi-square table, the value of chi-square table, which is 16.93. And then we can find out the chi-square count by adding up e minus o squared divided by e, which is 4.729. And then we can draw the conclusion, which is spelled to reject.
Now let's take a look at two-way table. Two-way table is very similar to the one-way table. The only difference is that two-way table is a classification with respect to two factors, so it requires a few more steps to do. There are two equations of two-way table. The first one is what we use to calculate expected value, which is row total times column total over grand total. And the second one is about how to find the degree of freedom. The steps are just like same template with one-way table. Firstly, we make HO and HA. Draw the graph and shade the rejected region. In this case, HO is always that the row is independent of the column, and HA is that they are dependent. And then we find the value of chi-square chart and chi-square core. If chi-square core is inside the shaded region, we say that we reject the null hypothesis. But if it's not, we say that we fail to reject the null hypothesis. And here's part of the chi-square chart. Remember that degree of freedom in two-way table is equal to number of row minus 1 times number of column minus 1. Now let's see an example from our homework. In the question it says that this table gives the amount of money invested in mutual funds according to 3 types of investment vehicles. Is the amount invested independent of the investment vehicle? Use alpha equal to 0.05. If there is a value of alpha in the question, we use whatever we are given, but if we couldn't find alpha in the question, we just use 0.05 as the default value. To solve this problem, we should follow the steps. So firstly, we make HO, which is amount invested, is independent of investment vehicle. HA is that they're dependent. Draw the graph, find the chi-square chart, and shade the region. After that, we calculate row totals, column totals, and the grand total. And then use the formula to get expected values. We should notice that a whole number should be the observed value, and the decimal number is the expected one. And then make a chart to calculate chi-square core and find a point in the graph. It's clear that the value of chi-square core is inside the rejected region, so our conclusion is reject the null hypothesis. But sometimes we don't really need to calculate all data from the question, because sometimes we are already able to draw the conclusion during the halfway. For example, in this question, we could get the conclusion after we got the result of the first row, because 13.77 is already bigger than the chi-square chart, which is 9.49. And so we could skip the calculate works and directly conclude that we rejected the null hypothesis.
Hi everyone, now I'm going to introduce the F-test. An F-test is a statistical test in which the test statistic has an F distribution under the norm hypothesis. The name of the test was coined by George Snedeker in honor of Sir Ronald Fisher. Fisher initially developed the statistic as the variance ratio in the 1920s. It is most often used when comparing statistical models that have been fitted to a dataset, in order to identify the model that best fits the population from which the data were sampled. In this test, we compare the variation in two samples. The values of F distribution can be 0 or more, and the large values of F are the evidence against the equality of two population variance. To do the test, the two samples have to meet the following requirements. The first one is the two populations are independent. The second one is the two samples are simple random samples. The third one is the populations are normally distributed. Now I'm going to show you how to read from the F table. The first step is to find out the alpha. Then we can decide which table we're gonna use. Alpha is usually given in the questions. If it's not given, we can use 0.05 to find the F table. Then we construct a graph. Shade the region. The row in here is the numerator degrees of freedom, and the column is the denominator degrees of freedom. For this one, we can use the n1 minus 1 to find out which column we're gonna look at. For this one, we use n2 minus 1, and n in here is the sample size. This is the table for alpha equal to 0.025. We can follow the same steps to find the F table. Construct a graph, shade the region, and then to find out the numerator and the denominator. Use n1 minus 1 to find out which column we're gonna look at. Then we can easily find out the F table we need.
Hi everyone, I'm Jason and I'm going to show you how to solve some problems that involves us to compare variations within two samples. Now let us start with a more simple question that you might encounter in the exam that involves us to compare the variations. Now in these types of question, you will always have to create a table that looks like this. Now in this question, they have already given us with a table which is really easy for us to then test the claim of variation, HO and HA. Since they already give us both the samples and the number of trials or whatever the question says, and SX, the standard deviation of both sample 1 and 2, all we need to do is use the formulas to find FCal and FChart. To find FCal, we find standard deviation 1 square over standard deviation 2 square. Now standard deviation 1 is always the standard deviation that is greater than the other standard deviation. So in this case, since sample 1 standard deviation is 4.2 and sample 2 is 3.1, sample 1 is the standard deviation that you take in the numerator, and sample 2 is the standard deviation that you take in the denominator. And for F-chart, you just find the degrees of freedom for N1 and N2 and you look it up in the chart. So to find FCal, 4.2 square over 3.1 square, which is 1.83, and to find the F-chart, since they don't give alpha, we take alpha as 0.05. So since our n is 16 and 18 respectively, we minus 1 from each of them to find the degrees of freedom, which is 15 and 7. We refer it to the chart, to the F chart, and we find 2.3. Since you see that fcal 1.83 is less than fchart 2.30, we fail to reject. Now, this is more a complex question that you will most likely to encounter in the final or in any other exams, which involves us to compare the variation within two samples. So in this question, it asks us to test the claim HO and HA. Now, as you can see that they don't provide us with both the samples N or the standard deviation of Asian and non-Asian. So the first step for us is to create a table to find out the standard deviation and the N. So finding N, in this case it's really easy to find the number of quarters because it's already listed above. Math 10, Math 2A, Math 1D, Math 1C, Winter Math 10, Winter Math 43, and Math 212 fall. So there's a total of 7 quarters, so we take N1 and N2 as 7. Now to find the S standard deviation of Asian and non-Asian, it's more tricky because you have to create a separate table and use the calculator to get the standard deviation. So to create the table, let's start with creating a table for Asian. Now you have to list every number that is visible in the given table and the number of times that the number occur. So for example, in this case, 16 occurs 1 time, 14 occurs 1 time, 27 occurs 2 times, 29 occurs 1, 18 1, 7 1. So here's the table. So you just have to use the calculator, plug in the values in stats edit, and you test the variation to find the standard deviation, which is 8.20 in this case. And you do the same for non-Asian except with different numbers since different numbers are listed. So 7 appears 1 time, 4 appears 2, 9 appears 1, 11 appears 1, 22 appears 2. So use the calculator again to find the standard deviation and you get 7.74. So as you can see here, the standard deviation for Asian is greater than for non-Asian. So we know that standard deviation 1 is 8.20, which is Asian, and standard deviation 2 is 7.74, which is for non-Asian. Now we find that N1 is 7, N2 is 7, standard deviation 1, which is Asian, is 8.20, and standard deviation 2, which is for non-Asian, is 7.74. So we create the table that we see in the previous slides where you always have to create this table so that it's easy for us to find the fcal and fchart. So finding the fcal as standard deviation 1 square over standard deviation 2 square, which is 8.20 square over 7.74 square in this case, which gives us 1.12. And since they also don't give us the alpha again, we take it as 0.05. So the degrees of freedom would be 6 for both. We refer to the fchart and we get 4.28 as the fchart. So as you can see, 1.12 is less than 4.28, which means fcal is less than fchart. So again, we fail to reject.
Hi everyone, my name is Joyce.
My name is Rose.
Today we're going to discuss some formulas for the correlation parts. First, we're going to introduce the formulas for the least square estimate. As it says, you are given few points from relation of two correlation variables, and you want to find a line that goes to all those points, such as the sum or square of area of the list. You need to find the slope and y-intercept of the line. So first, how do we find the slope? There's a formula which is m equal to ssxy over ssxx. So for the numerator part, which is ssxy, is equal to sum of xi minus x bar times yi minus y bar. And for the denominator is ssxy xs equal to summation of xi minus x corner square. From the above formula, the y-intercept is b equal to y minus x times the slope. From the above formula, which is y hat equal to mx plus b, is the best fitted line to all points given. Let's look at the example here. Example 1, find the best fit line for those following points 1, 2, 2.2, 3.4, and 4.4. First, we make a chart, write down the xi and yi. And then we use calculator to find the x bar and y bar. After that, we subtract xi minus x we find the values for this, and the same as y, and then we find the sum. And then we can use the formula to find the slope. So for the summation xi minus x corner square is equal to 5, and summation of xi minus x bar times yi minus y bar is equal to 4. And the formula, which is SSXY minus SSXS, is equal to 4 over 5. And here's the slope, is equal to 0.8. And now, since we have the slope, we can use the center of mass to find the point, and plugging the point and the slope to the equation of the line, and we can find b. After that, which is y hat is equal to 0.8x plus 1.
Now we are going to look some examples for the best fitting line, or we can call it regression line. For these 4 given points, we need to find out what is the best fitting line. We know that the best fitting line is y equals to mx plus b. The m represents the slope, and in order to find out the slope, we need to know what is SSXY and SSXX. So the first step, we need to make a chart. We need to know what is x, x bar, x minus x bar, and y, y bar, y minus y bar. And then we can know the summation of x minus x bar squared and the summation of x minus x bar times y minus y bar, which is minus 3 and minus 1. And then we can know the slope. M equals to SSXY over SSXX, which is negative 1 over negative 3 equals 1/3. And then we need to know what is the B. So we just plug in the y bar, the slope we just find out, and x bar. So B equals to the y bar, which is 5.5 minus 1/3 of x bar, 3.5, equals to 4.33. So in this example, we know that the best fitting line y hat is 1/3 of x plus 4.33.
And now we're going to do one more practice. Here is the given point, and we're using that point to find the slope and b. Remember, the slope is equal to SSXY divided by SSXS, which is summation of xi minus x bar times yi minus y bar. And for denominator is xi minus x bar corner square. And then we use that formula, plugging, we do the same thing as before, so we can find the slope, which the slope is equal to 0.7. And we find the slope and plug in one more point, which is the center of mass, to find b. And then we can find the y hat is equal to 0.7x minus 0.1. Question A. What would be your expected value for y corresponds to x equal to 1.5? So we have the formula. So when x equal to 1.5, we plug the point into the formula. Minus 0.1 is equal to 1.05 minus 0.1, which is 0.95. This is the answer for question A. And for B, how much error will one get if find y for x equal to 2? And for the given point, when y equal to 1, x is equal to 2. But if we plug into the formula, which we found already, which is x equal to 2, what is y? Y is 1.3. And for the arrows, is going to be actual value minus expected values divided by actual values and times 100%, which is 1.3 divided by 1 absolute value divided by 1 times 100%, which is 30%. And for x equal to 3, arrow bounds equal to 2 minus 2 divided by 2 times 100%, which is 0%. Because when x equal to 3 is the center of mass, so is less changing and less arrows here. So this is the reason why the arrows here is equal to 0%.
The next one is correlation. Then what is correlation? A correlation is between two variables when the values of one variable are somehow associated with the values of the other variable. The next one is linear correlation coefficient. The linear correlation coefficient R measure the strength of the linear correlation between the pair quantitative x and y value in the sample. The formula to find R, it's very complicated, and it's equal to n times summation of x times y minus summation of x times summation of y divided by root of n times summation of x squared and minus summation of x squared times root of n times summation of y squared minus summation of y squared. The property of R measures the strength of a line relationship, and its value is always between -1 and 1, inclusive -1 to 1. The values close to 1, when it's close to 1, indicate that it's a good positive correlation. Values close to -1 indicates a good negative correlation. So the positive correlation should look like this. M is bigger than 0. A negative correlation will look like this. When x increase, y is x increase, y is decrease. The m is smaller than 0. You need to note that there's one more. The value near 0 indicates these two variables almost have no correlation. You need to know that the values of r is not affected by interchanging x and y, which means when you change the x into y and y into x, it does not affect the correlation. The second is the correlation is not affected by converting to a different scale. The third is it is very sensitive to outlier.
The next example is from the exam number 2. From this given data, we want to find out is there any correlation or not. The first step is we make our null hypothesis and alternative hypothesis. For null hypothesis is there is no correlation, and the alternative hypothesis is there is correlation. And then we can draw a line. Since we know that r should be from -1 to 1, and then we can shade the region. And then we need to look at the chart and find out what is r for 6, because the number of the data is 6, and the alpha is 0.05, and then we can get 0.917. And then we type in those data into calculator and find out what is the regression line. We can get y hat equals to 2122.57x plus 582, and then the r is 0.95. We know that 0.95 is in the shaded region. Since we know that 0.95 is in the shaded region, we can have our conclusion is reject the null. This is another example for correlations. Given these 4 points, we want to know is there any correlations, or we can say what R tell us. So the first step is we make our null hypothesis and alternative hypothesis. There is no correlation and there is correlation. Second, we draw a line, shade the region, and we know that R is from -1 to 1. And then we look up the chart for R. N equals to 4, and the alpha is 0.05. For this R is 0.95. And then we use our calculator to find out what is the best fitting line for this 4 points. We get y hat equals to 1.2x plus 1.3, and the r is 0.74. We know that 0.74 is not in the shaded region. We can have our conclusion, which is we cannot reject the null. Next, if we want to find out what is the error at 0.48 for our best fitting line, we plug in the 4 into our best fitting line and find out the experimental y is equals to 6.1. And the error is the absolute value of actual number minus experimental number over actual number. So we can know the error percentage is equals to 6.1 minus 8 over 8 equals to 23.75%. The same thing, If we want to find out what is the error at every point, we need to find out every experimental y in each x. So we plug each x in to get the y equals to 3.7, 4.9, 6.1, 7.3. And we use the formula to find out the error. For this one is 3.7 minus 2, 3 over 3, which is 23.33%. Second one is 4.9 minus 5 over 5 is 2%. For this one is 6.1 minus 8 over 8 is 23.75%. For the last one is 7.3 minus 6 over 6 is 21.67%. This is the end of our presentation. Thank you for listening.